Hey, good morning. This is Steve Beaudoin here at Purdue, and I'm delighted to talk to you today about this method that we've developed, which is a tool for simulating explosives particle adhesion. And this tool was developed in order to assist in the development of new traps that are used in swabbing hands and luggage and clothing to try to find trace explosives in primarily transportation security applications. I'm going to show you a little bit about the method and then give you a way to access the method yourself if you want to try to use it yourself. Okay, I'm going to go away for a little bit and I'll be back and forth throughout the course of this demonstration. Okay, so if our goal is to have a tool that will predict the strength of explosives particles adhering to surfaces, we would expect that the tool would relate the size of the explosive particles. It would relate the topography on the surface against which the particles are attached, and it would relate to the composition of that surface. So RDX particles against aluminum that has a brushed finish, for example. Now here's the problem. Explosives particles are not all created equal. So over here you can see some RDX, and you see these are sort of rounded. If you look at them, they have some flat faces, but they're mostly rounded. Then if you look over here at the HMX, these are not rounded at all. They all have flat faces, crystalline faces. So how do we describe the adhesion of both kinds of particles? That's the challenge. Okay. So what we would like are predictive models. Okay. So we'd like to just run them over here on our PC or on our phone. The problem is for an explosive powder over here, where we're trying to model the behavior of a snowball, for example, where every snowflake is a little bit different, a really rigorous model is going to take forever to run, and the only way it's going to work is if we have really inaccurate descriptions of particles. So we assume all the particles are spheres. Okay? And that's not going to be appropriate, as I just showed you, because spheres are not even the rounded RDX from the earlier slide. Okay? So the question becomes, how do we come up with a simple, quick model that we can use to describe this explosives particle adhesion so that we can use it in everyday life to design next generation traps? So what we're going to use is what's called the enhanced centrifuge model, and you can see that right here. So what we do is we know that we've got a difficult system of a rough particle on a rough surface, and we want to describe it in terms of the simplest system possible, a perfect sphere on a perfect flat surface. Okay? And if you're describing this case here on the right-hand side, it's a very straightforward model that you can calculate on the back of a napkin during breakfast while you're having your coffee. It's related to this constant, which has to do with the composition of what's in the system, the size of the particle, and the separation distance of the particle from the surface. And that's it. Very simple and straightforward. You can calculate that with no difficulty at all. So what we're going to do is we're going to modify that constant and take all of the interesting stuff about this roughness and this topography and these shape variations and bury all of that in this constant. I'm going to spend a little time now showing you how we do that. But once we get that constant for a given explosives powder and a given surface, then we can describe all of the particles in that explosive against that surface in a very simple way. So that constant ends up looking like the true Hamburger constant, which is perfect for a system. It doesn't change as a function of size or shape. And then some correction factor. And that's what we're really going after. Okay. And I just show you that right here. That correction factor is a function of the roughness on the particle, the roughness on the surface, the shape of the particle, and its size. So if we have these Hamburger constants, these perfect Hamburger constants, if we had perfect spheres, those so perfectly flat spheres, those Hamburger constants would be constant, not a function of particle diameter at all. But in the real world, the powder has a whole bunch of interesting surface properties that cause these Hamburger constants to change as a function of the size of the particle and the composition and topography of the surface against which the particle is adherent. So we are trying to find a way to develop this map right here. Okay? So we're going to use the centrifuge method. We put a bunch of explosives particles on a surface. We look through a microscope and count them, measure their size, and then we put that surface in a centrifuge to cause the particles to come off, which I'll show you in just a minute. Then we look and we count them again, and then we put them back in the centrifuge, let some more come off, and we look and we count them again until we don't have any more on there at the end. And then we make a plot of the fraction of the particles that are remaining on the surface as a function of the force that was used to remove the particles. So we're going to put a bunch of explosive particles on the surface. We're going to dust them on. And then we put that under a microscope, and the operating spot is right down there. And you can see we've got a picture of this is in case ABS plastic plate. And there's a bunch of particles on that plate, and we count them using some software that comes with the microscope. Okay, and so then the student does that work. And after that's done, you take this plate that has the particles on it, and you get a centrifuge tube that has a special groove machined in it right here. And this plate goes inside that tube. Okay? And the reason for that is when the centrifuge tube is in the centrifuge and the centrifuge is rotating, this plate is going to be parallel to the axis of rotation of the centrifuge. Okay? So here we go. Here's a student putting that plate in the centrifuge tube. And there it is. It's just lovely. It's sitting right in there, just like that, anchored in place inside the centrifuge tube. All right. Now you can see in a typical centrifuge, the tubes go in at an angle. So when the tubes go in at the angle, the plate now rests parallel to the axis of rotation of the centrifuge itself. When the centrifuge is rotating, the particles are adhering, but yet there's an inertial force being applied that's pushing the particles off the surface. And that inertial force is related to the rotational speed of the centrifuge and the size of the particles and the distance of the plate away from the center of the centrifuge. It's a very simple mathematical expression. So there we go. We put the centrifuge tube inside the centrifuge. We rotate it, and we go through and do what I just showed you a moment ago in terms of getting the fraction of particles remaining as a function of force. The historical centrifuge method would just look at the condition at which 50% of the particles were remaining and then say, okay, that's it. That's the average adhesion for the explosive against the surface. Well, that loses all of this important information up here and all of that important information down here. And in particular, it's this information that really matters because these are the toughest particles to get off the surface. So again, we're going to go back and we're going to measure the adhesion of the rough powder against the surface, and we are going to find a way to extract these constants so that we can describe the adhesion using a nice simple model. So here is some data. This is the percent remaining as a function of rotational speed of an RDX powder against a stainless steel surface. And what you see here is that we have this drop in the adhesion between the powder and the surface, this drop as the rotational speed increases. So that is our experimental curve. Now, if we model all of the particles on that plate as perfect spheres, and we know using the microscope what the size of those spheres are, and we choose one Hamburger constant to describe the whole thing, we get behavior like this. We way under-predict the expected removal down here, and then way over-predict it up here. Well, that's not very good. So what we're going to do is adjust those Hamburger constants so everything lines up perfectly. Okay, so we didn't get good agreement at first, but if we look and we say, all right, at the first rotational speed increment that we used in our centrifuge, which maybe was 1,000 RPM, we removed 30% of the powder. So then we go down here to our bin, and we choose our size distribution of our powder that's on our plate, and we say, all right, I'm going to look at where the first 30% came off, and I'm going to choose the average size of the powder in that first 30% of the distribution, and I'm going to fit a Hamburger constant to that particular size. I'm going to assume all the particles that came off in this one step right here were of this average size. Okay? And then I'm going to do it again, and again, and again, and again, and again for each step size of rotational speed that I took, and I'm going to break up my size distribution again, and again, and again, and again, and again. So every one of these steps on the left-hand side corresponds to powder coming off the surface that has an average size from the distribution. Okay? And if I do that, now I know the size of the powder coming off at each rotational speed, and I can fit this Hamburger constant, so that I get outstanding agreement between the predicted adhesion and the measured adhesion. Okay? And now that I've done that, I can then plot my Hamburger constants, as I'm showing you right here. And this distribution of Hamburger constants describes the behavior of the entire explosive powder against that stainless steel surface. And now if I want to see, well, what happens if my explosive powder gets larger or smaller, or what happens if my surface gets rougher or smoother, I have a tool that I can use that describes the changing adhesion force. And it's a very simple tool with a very simple mathematical construct. And it will work over and over and over for all kinds of different surfaces. So now we know these effective Hamburger constants. We can predict the adhesion of the explosive powder against the surface we care about. And when we compare different effective Hamburger constants, we can rank the adhesion of the explosives against different surfaces. We can figure out which ones are the hardest to remove. And then we can design traps that explicitly go after the toughest, most strongly adhesive particles. So if you want to do this, reach out to me. You can reach me by email, or you can reach me on the telephone. And we've got the software. We'll give you the software so you can do this. We'll teach you the method. And you'll be able to develop these distributions of effective Hamburger constants, and then you'll be able to predict how explosive powders you care about adhere to all kinds of different surfaces, including traps and including surfaces that you're interrogating to look for trace explosives residues. So thank you very much to Alert, to the Department of Homeland Security for the support to do this work. We really appreciate it. I hope you enjoyed today's demo, and I look forward to answering your questions. Thanks very much. Bye now.